Okay, so getting ready here. Let's make sure. Pause recording. Okay, so it looks like it's going at this point, hopefully. All right, so we're going to be discussing titration material here. This is the PowerPoint portion that you would have seen in a YouTube video. We're going to go over it, and then we're mostly going to spend the time on calculations. I have the timer on my phone set to go off at 1:05 so that I don't run too close to the quiz and I can field any additional questions. All right. So what is a titration? At this point, you should be familiar with them. We've done them and talked about them in Chem 111, and we have also now done several of the Beyond labs using titration. So specifically, because there's more than just acid-base, but an acid-base titration is going to involve slow addition of one solution that's at a known concentration. We call that the titrant. That's usually what's in your burette, to a second solution that's of an unknown concentration. And you want to determine what the concentration of that unknown is. Now, there's other questions that can be asked, such as what's going to be the given pH after a certain amount of titrant is added, and we'll see examples of that in the math. Right, the reactions can either be measured by qualitative color change. That's when we use our indicators, so methyl orange, phenolphthalein, something of that nature. All right, and qualitative means it's just visual. It's not actually a mathematical equation, although they do have general pH ranges. Okay, and then if you wanted to get more quantitative, you could take a look at what we've been doing recently, which is using a pH monitor and monitoring the pH as you continue to add the titrant. Right? And then in addition to that, you can also use both. So it's very common to use an indicator so that you have visual cues as to how far your titration has proceeded, and then you use the pH monitor alongside with it in order to continue with that. All right, so one of the most, if not the most important point is going to be the equivalence point when you're dealing with your titration. So this is something in your labs you are asked to identify. The equivalence point is going to be when all of the moles of acid or base that you are titrating has been consumed by the titrant. So for example, if we have a weak acid, such as acetic acid, and then I'm titrating a strong base, such as sodium hydroxide, the question is, at what point do I have all of the acetic acid consumed by the amount of sodium hydroxide that's been added? So all of the acetic acid has now become the acetate ion or the conjugate base. That exact point is known as the equivalence point, okay? So when an acid is being mixed with a base and you finally hit that point, that's the equivalence point. And when you see it on a graph, a titration graph, you're going to see this large jump. Now, if it's an acid and you're titrating with a base, you're going to see it going from this slow climb for pH, and then suddenly it's going to go up very rapidly. And in the middle of that vertical jump, that is your equivalence point. Now, if it's a base and you're adding a strong acid to it, you're going to see it start at a higher pH because we're basic initially, and then it's going to come down like it drops off a plateau, and then it's going to even out. And again, that very middle point there, that is the equivalence point. All right, so the equivalence point is pretty easy to spot when you have these graph titrations. If you don't have a graph, you can still calculate it by finding the moles of acid that you're starting with, and then calculating the moles of base that would be needed to neutralize that. And then based on the concentration of that base, the question is how much volume or how many milliliters are you going to add with your burette, okay? So for monoprotic acids, we're going to have a single equivalence point. And if you've been working with your lab that's going to be due tomorrow, we're going to have polyprotic acids, all right? Specifically, I believe the lab tomorrow is a diprotic acid, the one that's due. But we've talked about diprotic and polyprotic acids in class. You have multiple Kas. And because you have multiple removable protons, you're going to be able to remove one and then remove another. So you're going to have two equivalence points, right? Or three if you have a polyprotic acid with 3 removable protons. So we can see this comes straight out of the OpenStax book. This is visualizing the equivalence point here. So you have titration with a strong acid. When you're dealing with a strong acid and a strong base, because these are both sodium hydroxide, strong acid and strong base, the pH will always be 7 at the equivalence point because it's a neutralization reaction. Okay, now here we see a weak acid and we have a strong base, sodium hydroxide. So you can see a couple things. First of all, the pH of the solution starts out higher. And that's because in the example on the left with a strong acid is going to have more hydronium generation, and therefore it's going to have a lower pH when it starts, around 1 here versus 3 in the other example for the weak acid. Okay, then we move along. You can see that it's a more drastic climb for the strong acid, whereas the weak acid, we sort of ramp our way up to it slowly, but then there's still this part in the middle where we do hit that equivalence point. Okay, but in a weak acid strong base, once you pass the equivalence point, it's not neutral, it's actually basic. And that's because a weak acid is going to be, when it finally hits that equivalence point, you're going to have slightly more base or hydroxide in solution, okay? Based on that conjugate base that's forming, versus a neutral where you're just making a salt and water. So for instance, hydrogen or hydrochloric acid and sodium hydroxide come together to make NaCl, sodium chloride, and water. That's salt water is a neutral type of solution. All right, so just to reiterate this and the different varieties we can have. A strong acid and a strong base, when they hit their equivalence point, will have a pH of 7. A weak acid and a strong base are going to have a basic equivalence point. The pH will be slightly above 7. When you have a strong acid and a weak base being mixed together, the acidic equivalence point is going to be slightly below 7. And then the one that really can be up in the air is if you have a weak acid and a weak base being titrated together. In this case, you have to look at the Ka and the Kb independently. So Ka and Kb, they are both representatives of how strong an acid is and how strong a base is. So in that case, you have to look at, is the Ka a greater value or is the Kb a greater value? Because that's going to determine what will predominate when you get to that equivalence point. Will it be the acid or the base as far as the strength? All right, so this leads into the Henderson-Hasselbalch equation. If you watch the video on buffers that came before this, we already outlined that and discussed it. We're certainly going to be utilizing it in our calculations today. All right, the Henderson-Hasselbalch equation, okay, is very important when we're dealing with weak acids, because when a weak acid is titrated, if you know where the equivalence point is, you can also find where the pKa level is. The pKa is going to be equal to the pH at the halfway point for your equivalence volume. So let's say that it takes 30 milliliters of sodium hydroxide to reach the equivalence point, then I can go over to 15 milliliters of sodium hydroxide halfway. And if I go up and I find where the titration curve is, and then I go across and I find where the pH is, the pH at that 15 milliliter mark will be equal to the pKa of that acid. Now, this only works for weak acids, all right? If you have a strong acid, you can't do this. So the reason for this is when I initially start, before I've added any base to head to the equivalence point, I have all of my value down in HA. I have not generated any A minus. But once I have gone through half of the HA, meaning I've titrated half of the whatever that weak acid is, then exactly half of it has been converted to A minus, or the conjugate base. And when this half-half ratio occurs, it means I have equal amounts of the acid, the weak acid, and the conjugate base sitting in solution. Well, that means if they're both equal to one another, they're going to drop out and become 1. And the log of 1 is going to be 0. So the Henderson-Hasselbalch equation at that point, all of the concentrations drop out in the logarithmic portion, and we get pH is equal to pKa. That only happens with a weak acid, and it only happens at the halfway equivalence point. All right, but it is very useful when you're working with this. Now, this was something that was asked of you. You may have not understood it completely in the Henderson-Hasselbalch equation, but when you had to do your lab, the previous one for titration lab 1, it said, find the equivalence point, circle it using the annotations or hand draw, and then go to the halfway volume and circle that. And then it said, that's your pKa. This is the reason for that, mathematically speaking. All right, so this is the last slide here before we're going to break out. This is sort of representative of what you might have been doing in your lab when you were doing, and it'll be representative of part 2, but you're going to have 2 equivalence points when you work on your lab for tomorrow. Okay, so you have an equivalence point that you identified approximately halfway to the jump there. And then if you go and you look at the volume that's half of that equivalence volume, you come up where the pink line is, that is where we find a pKa. Okay, now you can see the buffering region is sort of on that narrow, gradual slope that's right in the middle of the pKa. And typically it can go about a pH range in either direction when you're dealing with a system. So if the pK is 4.8, the buffering region is probably somewhere approximately around 3.8 to somewhere approximately around 5.8. And after that, you're going to start to lose your buffering ability. And if you're confused about that, go watch the buffering lecture that's on YouTube. It discusses in more detail about ratios and how you need to keep at least a 10% or greater ratio between the conjugate and the acid in order to have that buffering ability. All right, so at this point, I am going to bring up the calculations. And remember, I do have the timer set, so I at some point will stop and I will take any questions, but I do want to get to some of these calculations. So at this point, let's go ahead and minimize this, and I'm going to bring up the whiteboard. Just making sure, can everybody see my whiteboard that's up on the screen at this point? Okay, I'm seeing nods, so it seems like yes. All right, so let's take an example, and we're going to calculate some different variables for a titration. Right? So we have a titration. Let me select a color we can work with here. We're going to have a titration that involves 50 milliliters of 0.250 molarity formic acid, which is HCHO2. This is a monoprotic acid. Okay, and we're going to titrate this with some sodium hydroxide, and it will be titrated with 0.250 molarity sodium hydroxide. All right, so what I'm going to do is go along and ask some questions here. All right, so the first question that I'd like to know is what is going to be the initial moles, not molarity, but the initial moles of the formic acid. And the reason I want to know that is because I'm going to need to keep tabs on that as I move through my titration. Because if I know the moles I start with, then every time I add a certain amount of sodium hydroxide, I can look at the moles of sodium hydroxide and I can just simply subtract that from the initial moles, and I'll find out how many moles of the formic acid are remaining. So in order to do that, I have a concentration and I do have a total volume for the solution. So I can simply set it up by saying what volume I have in liters, which is going to be liters, right? Because we had 50 milliliters. I'm keeping this extra 0 for sig figs because it was attached here in the digit. All right, times the concentration. So the concentration is 0.250 molarity. Okay, you can also write this as 0.250 moles over 1 liter. The liters cross out and you end up with moles, if you know what molarity is. So the answer to this would be 0.0125 moles of formic acid. Okay, so nothing too difficult here. This is definitely Chem 111. You should be able to take molarity and convert into moles, use liters, go back and forth. All right, so here's the next question that I have. I know I'm working with sodium hydroxide, and I know that it has a concentration of 0.250. So what I'd like to know at this point is going to be, when will I hit the equivalence point? Okay, so when will the equivalence point occur? And this is going to be based on volume. So if you notice up here, I just tell you, you have sodium hydroxide at a certain concentration. So now what I'm saying is, how much, what volume of sodium hydroxide is going to be required in order to get rid of 0.0125 moles, all right? So what we're going to do is we're going to say, all right, I want to neutralize 0.0125 moles. So that's how many moles of sodium hydroxide I need. All right, now, the concentration of my sodium hydroxide is 0.25 molarity. Now in this case, I want to get rid of the moles because I need to find out the volume. At what point will the equivalence point occur. So what I do is I say every 1 liter of the sodium hydroxide will contain this many moles, okay? So that comes straight from the concentration. What I'm really doing is taking 0.0125 and dividing by the molarity of the sodium hydroxide, right? Moles will cancel. That'll tell me how many liters and therefore how many milliliters I need. So you put this into your calculator and you come out with 0.0500 liters. So I need 50 milliliters, okay? And if you look, this makes sense because sodium hydroxide is monobasic, formic acid is monoacidic or monoprotic. So it's going to be 1-to-1 when they react. So if they're at the same concentration and they go 1-to-1, then I'm going to need the same volume of the sodium hydroxide to neutralize it. Okay, so just making sure that our math makes sense there. All right, so let's ask an actual question outside of some of this hypothesizing. So let's say we want to know what is the pH of the formic acid, okay, before titration. So what does this mean? It means I want to know the pH of the acid that's sitting there before I ever add sodium hydroxide to it. And then the next step will be, let's add some sodium hydroxide. So we're technically still not doing any titration math right now. This is the type of math we've been working on the past week, okay? So what I would need to do is set up an ice chart here. What I would do is I would say, I've got formic acid, okay? I'm not adding any hydroxide, so that shouldn't be in the equation yet, right? Aqueous, I'm gonna cut out the water because liquids don't come into equilibrium, right? And then it's gonna generate hydronium. That's what I need the concentration of if I wanna find pH. Plus, I have the conjugate, which is going to be the formate ion, and that will be CHO2 minus because it's monoprotic. So if I lose an H plus, then it has a minus charge left behind. All right. So we set up ice for this and we say ice. Okay. And we've got an initial concentration of 0.250 for the formic acid, and it's obviously 0 and 0 over here at the starting point. So we're going to lose some amount X, we're going to gain some amount X, gain some amount X. Okay, and then the equilibrium is going to be 0.250 minus X, X, and X. So the two products, we've got two X's. So that's going to be X squared up in the numerator of the expression. Now, what I would need to do at this point is head over to a Ka table and grab the Ka, okay, for this compound here. So if you get the Ka, it's going to be 1.8 times 10 to the negative fourth. And I'm going to set that equal to X squared because it's products, and I have X and X, over 0.250 minus X. Now what I'm going to do is utilize the 5% rule, and I'm going to get rid of that. Okay, so if you go ahead and you proceed forward with that, you need to multiply by 0.250, and then you need to take the square root of that corresponding value. If you do that, you should find that X is going to equal 6.7 times 10 to the negative third. So what I need to do with this value is, this is X. X is going to be equal to H3O plus, right? And if I take a look, 6.7 times 10 to the minus 3, if I take that over 0.250, I definitely am within the 5% rule. I'm not going to run through that calculation right now, but this is small enough compared to 0.25 that I would not violate that. So I'm good to go. But remember, you need to check your 5% rule, right? So if this is the hydronium concentration, all I need to do is take the negative log of this, and I'll end up with pH. So this should obviously be below 7 because I'm working with an acid. If you take the negative log of 6.7 times 10 to the minus third, we come out with 2.17 as the pH. All right, so that is the pH of the acid. Now, if I add sodium hydroxide, which is going to be the next step that we take a look at, it only makes sense that this value needs to increase. Because if I use sodium hydroxide, if I'm introducing base to the solution and I'm getting rid of acid, shifting the equilibrium, it would only make sense that this needs to increase as base is being introduced. It's becoming less acidic as I introduce sodium hydroxide, not more. All right, so let's move to the next phase then. We have the pH of the initial. So let's pick a volume and say, what is the pH at 10 milliliters of sodium hydroxide added? Okay, so we have the initial acid. We add or titrate 10 milliliters of sodium hydroxide. Just as a reminder, the sodium hydroxide concentration is this. That was up in the initial problem. So the question is, what becomes the pH of the solution once we get to that point? All right. So what we need to do is we need to first consider, well, how much NaOH was reacted? Because we know however much NaOH reacted, that's going to be the amount that we remove from the initial formic acid. So I would say I've got a concentration of 0.250 moles for every 1 liter. That's the molarity of it, right? And then if I move forward, I said I used 10 milliliters of this. So let's convert that into liters, minding the significant figures. Okay, the liters will drop out, and I'll find that I have used 0.00250 moles of sodium hydroxide. So that's the number of moles that need to come off the initial amount of acid. Now, let's save ourselves some work because we already calculated that up here, right? One of the first questions we asked was, I gotta go way back up here. What was the initial moles of the formic acid? We found that it was 0.0125 moles. So what I need to do now is take 0.01225 and subtract 0.00250 from it, because that sodium hydroxide, that's the amount of the acid that was neutralized and brought over into a conjugate base form. Okay, so what we're going to look at here then is the reacted formic acid. So I have 0.0125. This is the initial formic acid. We already calculated that at the beginning, right? And from that, I need to take the amount of sodium hydroxide because that's how much reacted. 0.00250 moles. And if I do that, I end up with 0.0100 moles, okay, of formic acid. So let's consider what all of this is here. This is the formic acid that is left in solution. This is the amount that actually reacted. Okay, everybody following along? So if I know that this is monoprotic, then this value is not just the amount that reacted, but it also becomes the amount for the conjugate base, right? So for every single mole of formic acid that I reacted with sodium hydroxide, it creates a mole of the conjugate base. So this is the value that we would need to use at 10 milliliters for the conjugate base. So now we're starting to gather some values here. We can actually move forward. Okay, so what we need now is the Henderson-Hasselbalch equation in order to properly tackle this. So what we're going to say is it wants the pH with 10 milliliters of the sodium hydroxide added. So pH is going to be equal to pKa plus the log of the formate ion, because it's product over reactant, right, over the concentration, of the formic acid. All right. So we can figure out what the values to plug in here are. The pKa is going to come from the Ka, which we already grabbed in a previous part. So the Ka was found to be 1.8 times 10 to the negative fourth. So all I have to do is say the negative log, okay, of 1.8 times 10 to the negative fourth. And that gives back 3.74. So there's the pKa value I'm going to plug in to the Henderson-Hasselbalch equation. Now the question is, what values get put up here? Well, since all of this is sitting in the same solution, I don't technically have to convert to molarity. I can just use the mole values here and plug them in. So the moles, okay, of the formate ion over the moles of formic acid that are in solution. So let's set this up. It's going to be pH equals 3.74 plus the log of, okay, now it's the formate ion, so 0.00250 over 0.0100. Okay. You put that into your calculator and you'll get the pH back. Okay. Now remember what we said, it needs to be higher than the initial pH. So when I did this and I put it into my calculator, I ended up with 3.14 as the pH. If we go back up and look at the initial pH, it was 2.17. So that makes sense. I've added some base and I have increased the pH as I've introduced more conjugate base to solution. All right. Now, we're starting to approach the 105 mark. So I want you to think about this, but we're going to go over the math for this part tomorrow. All right. So what happens when we are at equivalence point? So now the question is, what's the pH when 50 milliliters of NaOH has been added? Right? Now, here's what I want you to think about when we're looking at this. You can no longer, unfortunately, rely on the Henderson-Hasselbalch equation, because this says that pH is equal to pKa, all right, plus the log of, and I'm just going to abbreviate here for the sake of time, A minus over HA, right? So it's formic acid, or the formate ion over formic acid. All right, well, at equivalence point, what does HA equal? 0. What happens when you put 0 in a denominator? It errors out, right? You can't solve that. It essentially could go to infinity. So the problem here is that you're going to throw into the Henderson-Hasselbalch equation an error with the logarithmic function, and then it's just going to give you an error for your pH. So what we're going to start with in class next time and take a look at is, how can I get around this? I'm used to the Henderson-Hasselbalch up to the equivalence point, and it is useful. It will work for that. But once I hit the equivalence point, how could I find the pH when I don't have any of the acid left? And I'll tell you, the answer is going to lie in the fact that we now can only have concentration of A minus. So I'm going to need to use a Kb instead of a Ka, or a pKb instead of a pKa to start. And then I'm going to have to use Kw, because we're dealing with conjugates, to find the values that I need. All right. So we will get to that tomorrow, but here I'm going to pause it because I've got about 1 minute left on my timer. All right. So I am going to stop recording this so I can post this part to YouTube, and I will open it up to questions at this point.